So in this video we are going to continue the discussion on the problem that is shown here, or the system that is shown here. The system consists of a surface which has varying radii of curvature, and there is a disk that is rolling without slipping on this surface. The disk is of course circular with a radius small r, and it is given that the point of contact O prime is the point of contact associated with the ground, with the curved ground surface at any instant. That point of contact is moving with a constant velocity v0, which is always tangential to this curved path. So this is one configuration of the disk, and sometime later this is the configuration, and you can see that O prime is still it still has a velocity of v0 tangential to this surface. Now the point P is an arbitrary point on the circumference of the disk, and at this instant it is making an angle of theta, or QP, where Q is the center, is making an angle of theta with this line. Now this line is the line joining the instantaneous center of curvature of the path with the center of the disk, and that line passes through the point O prime. So the angle theta is made by QP with that line. So as we can see here in this configuration, CQ still is that line which joins the instantaneous center of the surface with the center of the disk, and it passes through the point O prime. And at this instant the point P has turned by a greater angle theta as the rolling without slipping is taking place. So this is given, and we are asked to find the velocity and acceleration of the point P. Also we are asked to use this this coordinate triad, which consists of the instantaneous unit vector pointed along CQ from Q towards C. That's the direction of, and that's En, that's the normal unit vector, and we have the perpendicular tangential unit vector Et, which is always going to be parallel to the V direction, or V0 direction, because it is tangential to the curved surface. And the binormal, so this is a NT coordinate system, the binormal unit vector accordingly is going to be pointed perpendicular to the page pointing downwards. So we are asked to use this triad, and capital R, by the way, is the instantaneous radius of curvature of this curved path. So R is this distance C to O prime at the initial, not at the initial, at this arbitrary instant, and then R becomes this, it is again C to O prime, but the distance changes because of the radius of curvature changing along this path, and this is the instantaneous radius of curvature at this instant. So it's represented by capital R. So we have worked on this problem in the past few videos. Initially we started by through this video we are trying to demonstrate the use of different rotating reference frames, and how the same problem can be solved using different rotating reference frames, so that we clarify this idea of rotating frames. And in the process we are also trying to distinguish rotating frames from the triads that are used to express vectors. In the previous parts, the first two parts, we used the rotating frame, a rotating frame that is attached to and fixed to the disk. So the rotating frame's angular velocity was the net angular velocity of the disk, and accordingly we derived the velocity and acceleration. In deriving the acceleration, we showed two methods. One is of course the use of the rotating frame equation, the 5-term equation that is, and the other is to do a direct differentiation of the velocity, and we verified that both yielded the same answer when done correctly. In the last part or the previous part of this problem, we said that we are going to change our rotating frame of reference. We are now going to consider the rotating frame of reference to be fixed to CQ. So as the disk rolls without slipping and CQ is changing, that is going to be our reference frame, based on which we are going to write the 3-term velocity equation and the 5-term acceleration equation. So here the angular velocity of the rotating frame is essentially the angular velocity of CQ as the motion takes place. So with this new reference frame, in the third video, which is the previous video, we derived an expression of the velocity of the point P, and we showed that again, if we follow this approach correctly, then we get the same answer as before, because we are still expressing all our vectors in terms of this triad. So this triad has been a common triad which was used in all the parts of this problem. In this video, what we'll do is we will complete the derivation of the acceleration of the point P. We will, of course we can do direct differentiation, but that is already done. So we are going to use the 5-term acceleration equation, and we are going to show that with this rotating reference frame we still get the same answer as before, as long as we follow the principles and the concepts of rotating reference frames correctly. So with that, let us start working on the acceleration expressions. So here is the setup of the problem, and we want to find AP, and we recall that when we used the rotating reference frame to be CQ, then then we expressed the velocity of P with respect to O prime, and that is because with the rotating reference frame fixed to CQ, that was a more natural choice. We could have still chosen Q as the point about which we express the velocities, but then when you combine it with the angular velocity of the rotating frame, it becomes a little bit challenging to or cumbersome actually to express all the vectors. So that's that, and so then the equation that we have is AP is equal to AO prime plus omega dot cross rho P with respect to O prime, and you see P with respect to O prime is shown by this vector here, sketched in red, minus omega squared rho P with respect to O prime plus 2 omega cross rho P with respect to O prime, or rho dot actually, in the rotating frame, plus rho double dot P with respect to O prime in the rotating frame. A couple of things here. omega, always when we use these relative velocity and relative acceleration equations, is the net angular velocity, which is the total angular velocity, not any relative quantity, angular velocity of the rotating reference. And we have clarified this before. The reference frame and the triad are different things. The reference frame is the as the name suggests, it's the frame of reference in which we are going to perceive how the motion is taking place. Specifically, it is in this reference frame that we are going to find omega dot, rho dot r, and rho double dot r. So when we formulate this rho double dot r, omega and omega dot, we have to, that's when our understanding of the rotating reference frame becomes important. In contrast to this, the triad is a more mundane thing. The triad ET, E, and EB that is being used over here is more mundane in the sense that it is simply placed so that we have a convention to express all vectors. We have to express all vectors in terms of a single triad, because if they are not all expressed with respect to one triad, then what happens is that we cannot do vector operations, whether they are cross products, whether they are vector additions, and so on. So that is one point. The other point is that this term that we see over here, this is essentially minus omega squared rho p with respect to O prime. This is nothing but a simplification of omega cross rho p with respect to O prime. Okay, so this is one note and this is another note, and we know that this is true only when there is planar motion. Right? That's that. So now let us figure out what the different let us formulate all these different vectors on the right hand side. So what is the acceleration of the point O prime? Well, the point O prime is a point on the ground, and it represents the instantaneous contact point between the disk and the ground. The problem says that this point O prime moves with a constant velocity, and the direction of the velocity is always tangential to the curved surface. So you can see that O prime's motion is a curved motion. It follows a curve, and at any instant O prime is undergoing a circular motion about the point C. So since it is a circular motion about the point C with the C as the center, it therefore has a normal acceleration towards C, and so that acceleration is then going to be V naught squared over capital R, and it is going to be in the En direction. Right? So that's the centripetal acceleration of the point O prime. Now omega is, as mentioned here, it's the net angular velocity of the rotating frame. The rotating frame is CQ. It is the rotation of CQ that we need to now incorporate, and the net angular velocity of CQ. So what is the angular velocity with which the line CQ is turning? Well, that's also simple, because at this instant CQ is turning with C as the center, so the angular velocity is, and since VO is a constant velocity, so it's VO divided by capital R. That's the angular velocity. VO divided by capital R is the instantaneous, or is the angular velocity, or the instantaneous angular velocity, because r is changing. And it is divided by capital R because clearly VO is perpendicular to R, because VO is tangential to the surface. So it is VO divided by R, and it is clockwise if we are looking at this page, so it is in the EB direction. Alright, so that's the angular velocity. Now omega dot then is the rate of change of this term. Now EB is not changing in direction, so when we differentiate, we don't need to differentiate EB because EB dot is 0. V naught is also a constant parameter. The only thing that is changing here is R, because the radius of curvature of the surface changes. So when we differentiate, all we have to do is differentiate this expression with respect to R and incorporate R dot. So minus V naught over R square times R dot EB is the angular acceleration of the rotating frame. So we have that figured out. Rho p with respect to O prime is as shown here. This is this vector. It's quite easy to derive this vector. We have done it in the previous part. It is essentially r plus r cosine theta in the with a negative sign in the en direction, and r sine theta in the et direction, which is minus r times 1 plus cosine theta en plus r sine theta et. So let me just draw a divider here so that our discussions are, or our notes are clear. So that's rho p with respect to O prime. Now we still need to find out this vector and this vector, the relative velocities in the rotating frame. Keep in mind again that when the 2 points P O prime in this case, but whatever be the 2 points, when these two are on the same rigid body, and so there is an and here, when our rotating reference frame is fixed to the rigid body, when our rotating reference frame is fixed to that rigid body, then this term and this term become equal to 0, because the reference frame is fixed to the rigid body, and when it is fixed to the rigid body and rotating with the rigid body, then the 2 points do not perceive any motion with respect to each other. This is very similar to basically our perception. For instance, if a person is standing on the ground on earth and looking at a tree, then looking at a trunk of a tree, then the person will not perceive any motion of that tree with respect to himself or herself, because both the tree trunk as well as the person are standing on earth, and from the person's viewpoint, the rotating reference frame is fixed to the earth. Okay, the person's eyes are fixed to the earth, and as the earth turns, it does not therefore, the person does not therefore perceive any motion of the trunk of the tree. On the other hand, if let's say the person, or if the point of reference was let's say at the center of the earth, and the rotating frame, so there is an and here, and the rotating frame was fixed to the vector joining the sun and the earth, so the rotating frame is turning as the center of the earth turns, so it's turning with the center of the earth, then with respect to that frame, in that frame the trunk of the tree would still be rotating, because that rotating reference frame is not fixed to the earth rigid body. So a subtlety here. So here we need to calculate, and these two vectors, and they are not going to be zero. So how do we do this calculation? Well, we first impose that we are in this rotating frame. Fortunately, in this rotating frame, we see that ET and EN are not changing. Within this rotating frame, ET and EN are not going to change, because ET is always going to be perpendicular to this CQ, and EN is always going to be along CQ. So ET and EN are not changing inside this rotating frame. So therefore, rho dot P with respect to O prime is going to be found by taking the derivative of this under the condition that En and Et are constants. So we don't need to differentiate the unit vectors here. So what else do we need to differentiate? Well, small r is a constant, and then theta is the only thing that is changing. So we'll have r sine theta dot En plus r cosine theta dot Et. Now we have the expression for theta dot, and theta dot is V naught divided by let me just check, V naught divided by small r. This was derived in the prior discussions, so I'm not repeating that here. It was found out by imposing the fact that the point of contact on the disk is at a zero velocity instantaneously, and we know the velocity of the point Q, and so from there we are able to find out that theta dot is V naught divided by small r. Alright, so we substitute that here, and we have V naught sine theta En plus V naught cosine theta Et. Alright, so that's done, and we also need to derive an expression for the acceleration of P with respect to O prime in this rotating frame, and that will be found again by taking the differentiation of this vector. Again, since it is being differentiated within the rotating frame, or the velocity that we are seeking is within the rotating frame, so we are not going to differentiate En and Et. The only parameter that will be variable in this differentiation is going to be theta. So we'll have V naught cosine theta dot, which is V naught over small r En minus V naught sine theta times theta dot, which is going to be V naught over r Et. So this is going to give us V naught squared over r times cosine theta En minus sine theta Et. Right, so we have the acceleration. So now all we have to do, so we have all the vectors that we need to incorporate in this expression. So we are now going to just find out these individual cross products and this product here, and then we are just going to put everything together to get the overall expression of the acceleration. So it's algebra beyond this point. So first we are going to do omega dot cross rho. I just put the parentheses, but it doesn't have to be. Usually this is used when you are doing a derivative, but I just put this parenthesis by mistake. So minus V naught over R squared R dot EB cross rho P with respect to O prime. So it is cross minus R 1 plus cosine theta En plus R sine theta Et. Okay, so at this juncture we also need the rate of change of these unit vectors, and this was again derived in when we did the previous parts of the problem. So I'm just going to write the expressions without going over the derivations. It's quite simple actually, and you can go over the prior videos. Not the differentiation of the unit vectors, but the cross product of the unit vectors is what we need to just articulate here. So note that EB cross EB cross En is minus ET. The rate of change of the unit vectors when they were needed were derived in the prior videos, so but we don't need to do the rate of change of the unit vectors because we are already using the 5-term acceleration equation. So we need EB cross En and we need EB cross ET. So EB cross ET is En. Okay, so we have the cross product of the unit vectors. So our expression then is going to be V squared capital R dot small r divided by capital R squared. EB cross En is minus ET, so we'll have to put a minus sign here because the two minuses get multiplied prior. 1 plus cosine theta Et, and EB cross ET is En, so this will also have a negative sign. V naught capital R dot small r divided by capital R squared sine theta En. Alright, so we have that. We now need to find this negative omega squared rho P with respect to O. So let's do that calculation. Minus omega squared rho P with respect to O prime is omega squared. This represents the square of the magnitude of the angular velocity. So the magnitude is V naught over capital R. So we have negative V naught squared over capital R squared times this unit vector. So times minus R 1 plus cos theta En plus R sine theta Et, which is V naught squared small r over capital R 1 plus cosine theta En minus V naught squared small r over capital R. Oh, I forgot to put the square here. So capital R square in both terms sine theta Et. And let me just see if I have incorporated the signs correctly. Yeah, okay. And then we have to do this Coriolis term calculation. So let's go ahead with that. So we have 2 omega cross rho dot P with respect to O prime in the rotating frame. So that's 2, and omega is V naught over capital R EB cross the rho dot within the rotating frame. So that was determined here. So cross V naught sine theta En plus V naught cosine theta Et. So EB cross En is minus Et, so we are going to have minus 2 V naught squared over capital R sine theta Et, and EB cross Et is En, so we are going to have plus 2 V naught squared over capital R cosine theta En. Alright, so we have all the required terms here, and the last step then is going to be to just put all these terms together and determine the acceleration expression. So we'll do that the next page. Alright, so AP is then equal to AO, which is V naught squared over capital R En plus omega dot cross rho, so we will take that term here, that's the expression for omega dot cross rho. So minus V naught capital R dot small r over capital R squared 1 plus cosine theta Et minus V naught capital R dot small r over capital R square sine theta En. Then we need to incorporate this negative omega squared rho term. So let's incorporate that, plus V naught squared R over capital R squared 1 plus cosine theta En minus V naught squared R over capital R squared sine theta Et. Alright, then we have the Coriolis term. So the Coriolis term is minus 2 V naught squared over capital R sine theta Et plus 2 V naught squared over capital R cosine theta En. So we have that, and then finally we have to incorporate the this rho double dot R P with respect to O prime. We have the expression for that as well. So V naught squared over R cosine theta En minus V naught squared over small r sine theta Et. Okay, so we have put together all the terms. Now it's just a matter of rearranging. We can see that the unit vectors that show up are En and Et. So all we need to do is collect the terms that have Et and En in them. So let's put together the terms that have Et in them. So we have minus V naught capital R dot R divided by R squared 1 plus cosine theta. You can, when you are doing these derivations, it may not be a bad idea to just check the units to see if really what you are getting is an acceleration, or if not, then you have some algebra mistake probably somewhere. So here you have the velocity meters per second. This is in meters per second, and this is in meters, so it is meter cubed per second square, and here you have meter squared. So you basically have meter per second squared, which is the units of acceleration, and so we are good. So here we have this term, here we have to take this term here, V0 squared small r over capital R squared sine theta. Again, the units is meter squared per second squared divided by meter, so it's meter per second squared, so we are good. Minus 2 V0 squared over capital R sine theta. Again, the units are fine. And then minus V0 squared over small r sine theta, and this is in the ET direction. In the EN direction, we have V0 squared over capital R, this term. We have this term, which is V0 capital R dot R over capital R sine theta, that's in EN. Then we have this term plus V0 squared small r over capital R squared 1 plus cosine theta. Then we have this term here plus 2 V0 squared over capital R cosine theta, and then we have this term, which is plus V0 squared over r small r cosine theta. So all these are in the EN direction. Okay. If we just rearrange the terms a little bit, then we get the following. So we'll keep the first term the same. We'll combine the second terms, because you see that sine theta as a factor, V0 squared as a factor showing up. So V0 times capital R dot small r over capital R squared times 1 plus cosine theta. So we'll keep it as it is, and then we are going to put together V0 squared over small r sine theta. We'll factor that out, and within parentheses then we are going to have small r squared over capital R squared plus 2 small r divided by capital R plus plus 1, right? So this is our expression in the ET direction. In the EN direction, we will have minus V0 capital R dot R over capital R sine theta, and cosine theta term I think can be combined, so we will have, so then we will have plus, so I'm going to take this term and combine it with this term, so we will get V0 squared over capital R 1 plus r over capital R, small r over capital R. That is good. And then you see we have all these three terms that have cosine theta, V0 squared, and so on. So I'm going to just then do V0 squared cosine theta divided by small r times r squared over capital R squared plus 2 small r over capital R plus 1. Okay, and whole thing is in the en direction. So we note that this term, r squared over capital R squared plus 2 small r over capital R plus 1 is equal to small r over capital R plus 1 whole squared. So therefore our AP expression then is minus V0 capital R dot small r over capital R squared 1 plus cosine theta minus V0 squared over small r sine theta times small r over capital R plus 1 whole squared. This is in the ET direction, plus in the EN direction we will have minus V0 capital R dot small r over capital R sine theta plus V0 squared over capital R 1 plus small r over capital R plus V0 squared cosine theta over small r times small r divided by capital R plus 1 whole squared, and this is in the EN direction. And that's essentially the acceleration expression. That's the acceleration expression, and if you go back and check with our previous solutions, you will see that the expression matches exactly. And so so that's essentially the completion of what we wanted to do in this video. Essentially our goal was to show that by using a different rotating reference frame, many of these rigid body kinematics problems can be solved, as long as the concept of the rotating reference frame is clear to us, and we know the distinction between the rotating reference frame and the triad that is being used. So that is it for this video. Thank you.